Hi, and welcome to 8.1b Work 2. So we did the basics in Work 1, and we just get a little bit more into it in this lesson. So a couple different things. Students will be able to describe and calculate the work done on an object by a single force, just like before, but we'll introduce like a new spin to that formula that we have. Nothing crazy. The second thing, students will be able to determine if the work done is positive or negative. What the heck does that mean? And then students will be able to describe and calculate the net work done on an object when multiple forces are present. So just like we had a net force, you could have a net work. And I wonder if that positive or negative work thing is going to tie into the fact that there is a net work. All right, so this should look familiar. It's the slide from yesterday. Work is a scalar. It's equivalent to the force times the displacement. But what is the displacement equal to? Can you think of a different way to describe displacement to somebody using two different physical quantities from our reference table? Well, the very first formula we learned is v is equal to d over t. The average velocity is equal to the displacement divided by the time. And if you cross multiply, you get the fact that the displacement is equivalent to the velocity times the time. So in our equation, we can replace the displacement with velocity times time. And this is helpful if they give you in the word problem the force, the velocity, and the time, and you don't feel like using this formula to find the displacement first so that you can plug it in over here. It's just kind of a handy version of the formula that you might need to use as you do the problem. So yeah, it's the force times the velocity times the time. That'll give you a joule. How? Because Newton times a meter per second velocity times a second turns into, when you cross, not cross multiply, but when you cross these 2 seconds off, a second divided by a second cancels out. And then what are you left with? Just a Newton times a meter, just like before. And we define that as a joule. Just as a reminder, it takes about 1 joule of energy to lift an apple from your waist to above your head, which is about 1 meter. Very nice. So that formula for work, does it say FVT in your reference table? It does not. It does tell you it's equal to the change in the total energy, but if you want, you can write in equals FVT as a little shortcut. Again, if they give you the velocity and the time and the force and they're asking for the work. So let's do a quick example that looks like this. It says a student applies a 30 Newton force to push a 5 kilogram crate at a constant speed of 5 meters per second across a rough floor. How much work is done by the student on the crate in 6 seconds? So this force, how much work is done by that force? We'll write out our given information. That's all we really need to find the work. They do tell you the mass is 5 kilograms, and we can assume we're on Earth, but we're not going to need that stuff because we're just asking about the work done by this force. Okay, so we write our equation, substitute, and solve, and you get the work is equal to 900. What are the units for work? If you do a lot of work, you could buy a lot of joules. Okay, so 900 joules. Nice. Let's get into it a little bit more. So positive and negative work. Wait, I thought work was a scalar. How can work be positive or negative when direction doesn't matter, right? Scalar quantities, direction doesn't matter. We're not talking about a vector. You don't have work with arrows. And we've been using positive and negative to describe the direction of vectors. Yes, that is true. But don't forget, scalars can be positive and negative as well. Work is kind of an abstract scalar quantity. Let's use a different scalar quantity that you're more familiar with. You could have positive and negative money. Money is also a scalar. You can gain money or lose money. You could get positive $5 into your bank account. Yes, that's great. I gained money. Just like you could gain work or gain energy. But you could also lose $5. You could have negative $5. taken from your bank account. So yeah, scalars are positive and negative. Remember, before taking this class, you probably only dealt with scalars, and you did add and subtract scalars together. Then when we introduced vectors, we said, oh, let's use the positive and negative to help us mathematically describe the direction. So that is something that we can use, positive and negative, to describe the direction. But you don't have to, like we can still, as we said, use positive and negatives to describe scalars. Are you gaining or are you losing something? So by doing work on an object, you can either make that object gain energy and do positive work, or you can take energy out of the system by doing work on the object and you do negative work. So after we talk about work in this unit 8, then we talk about power, and then we talk more about energy. So energy will come up again, as we said before, in form of kinetic energy, gravitational potential energy, and elastic potential energy. So in all those scenarios, you could either gain energy or take energy out of the system by doing work. So this is an example I like to do in the classroom. I have what's called a constant velocity cart. So I have the cart moving across the table. All right, let's say the cart is moving to the right. So the displacement is to the right, and I can push. What I do is I exert a little bit of a force, and I push on the cart, and I make the cart go faster just by using my hand and pushing on the cart in this direction. So the cart was already traveling to the right, but I'm going to now exert a force on the cart in the same direction as its displacement. And as you can hopefully visualize in your head, as I push on this cart with my hand, I make it go faster, and I actually make it gain kinetic energy. It's moving faster, it gains kinetic energy. So when the force and the displacement are in the same direction, all right, you get positive work. You're gaining energy. You're going faster in this example. So if the force is in the same direction as the displacement, you're going to gain energy. And then this is why I like to use the constant velocity cart. I could also slow this thing down if I exert a force with my hand. Now I push on the cart in the opposite direction from its displacement. So the cart is still moving this way, but I want to slow it down, and I exert a force in the opposite direction of the displacement. And I slow it down. So that means it's not moving as fast. That means it lost kinetic energy. How did it lose kinetic energy? Because I did work on the system. I did negative work. So the displacement, again, in this example, we'll say it's pointing to the right. The cart is still moving to the right, but I'm opposing that motion. I'm pushing on that cart, and I'm taking energy out of the system. The system loses energy because I'm doing negative work. This force is doing negative work. Force is in the opposite direction as the displacement. So that's how we say we could have positive or negative work. We look at the direction of the force and the displacement. There's a little bit more to it than that, though. That's kind of the concept. How can we describe this mathematically? So yesterday we introduced how the work is equal to FD cosine theta. In those two examples I just gave, it was either all in the same direction or all in the opposite direction. But remember, we have the component of the force that's acting parallel to the displacement. That's where the cosine theta comes from. So in the following examples, the displacement vector is always going to be pointing to the right. All right, and this is just kind of an abstract way to describe the mathematical concept there. So the vectors that appear on the axes represent the direction of the force. So our cart, let's say, is always moving to the right. And in this case, we'll have also a force that's pointing to the right. Okay, and then what we're going to do is we're going to find the cosine of the angle. It says the sine resulting from the cosine between the displacement vector and the force vector. What is the angle right now between the force and this displacement? Is there an angle between them? All right, the sine that results from the cosine between the displacement vector and the force vector determines whether the work is positive or negative. The cosine of the angle will tell you if it's a positive or negative work. So in this example, hopefully you can see, it's a cosine of 0 degrees. There is no angle between these two vectors, so the angle is equal to 0. And if you plug in your calculator, or maybe you know offhand, what is the cosine of 0? It's equal to positive 1. So we could say we're doing positive work. And this agrees with what we said in the last slide, where the force and the displacement are pointing in the same direction. So you're like pushing the cart faster, you're making it go faster, you're making it gain kinetic energy in that example. Well, what happens if your force, now we're doing a different one. So now your force is up, your displacement is still to the right. What is the cosine of the angle between up and to the right? The cosine of 90 degrees is equal to 0. So this goes back to something in the previous lesson where we were talking about, oh, you need the component of the force, at least some component of that force to be in the same direction as the displacement to do some work. So no work is being done. 0 times FD, no work. All right, so what happens if it's pointing in the opposite direction? That angle is 180 degrees. And if you plug in your calculator the cosine of 180, you get -1. And then the math is telling you that you're doing negative work by doing the cosine of 180. All right, so it doesn't always have to be in the same exact direction. Oh, and then we could also do the cosine of this angle. So it would be 90, 180, 270. So what is the cosine of 270? 0 again. So no work is being done because it's not pointing. There's no component pointing along with the displacement. All right. Now you could have this angle here. So 90 plus a little bit. In this case, we'll call it the cosine of 135 degrees. And if you plug that in your calculator, do you think you get a positive number or a negative number? You get a negative number. So there's a component of this force vector that's pointing opposite the displacement. And the math knows that. So the math tells you, oh, that's negative work happening. It pops out a negative number. And in this quadrant, you could have, let's say it's cosine of 45 degrees. You plug cosine 45 degrees in your calculator, and the component of the force is positive. You get a positive number over there. So that's kind of just an overview of positive and negative work. Let's talk about network. And we're not talking about networking like interacting with people in social situations for your own benefit, which is a good thing to know how to do. It's a good life skill. But this is different, completely different. So if you're not good at networking with people, don't worry. We're talking about network. If many constant forces, many forces, are acting on an object like friction, gravity, and applied forces, you can find the net work done on the object by first finding the net force on the object. So instead of like finding the work done by each individual force and adding it all together, which you could do, you could first find the net force and then use that in your work equation, and that'll tell you the net work being done. And then just to make things more complicated, this is what we introduced today in the very beginning. Don't forget, you could replace the D with a V times T. So this is like a nice looking formula there. All right, example 2. I'm going to do this in 2 different ways, and I kind of described the difference in the previous slide there. So it says a worker pushes a 500 Newton crate, that means the weight, that the force due to gravity is 500 Newtons, with a horizontal force of 200 Newtons, that's the applied force, a distance of 25 meters. Assume the coefficient of kinetic friction between the crate and the floor is 0.3. Part A says, what is the frictional force? Then you could find the net force acting on the crate, and then you could say what the net work done is. So here, we're finding all the forces first before we find the net work. I like to start by drawing a free body diagram where we have the weight of the object, and we're going to have a normal force. We have an applied force, as shown in the diagram previously. They said that's 200 newtons. And there's a frictional force. We don't know what that is yet, but we know it's kinetic friction because it's already sliding. All right. Now the weight, they said, is equal to 500 newtons downward. that means the normal force is going to be equal to 500 newtons upward. And they also told you, oh, so we don't know what this is yet. They told you the kinetic friction, the coefficient of kinetic friction is equal to 0.3. We know we are on Earth, so we want to get points for that. And yes, so we can start by, if you wanted to prove where we got this from, I can make that equation. So that's just the sum of the forces in the y direction. And then we know the net force is going to be 0 there. It's not accelerating in the y direction. So F equals ma, and a is equal to 0. We're looking for the normal force minus 500 newtons. So that's just proving what we knew already from looking at the diagram. Okay. Part A wants you to find the frictional force acting on the crate. So we could say FF is equal to mu Fn, and we're looking at the kinetic. So you substitute in, and you solve. The frictional force is equal to 150. What are the units for frictional force? Newtons. I know some of you said joules. I almost said joules, but I didn't. All right, so the frictional force is equal to 150 newtons. All right, so now it says, what is the net force acting on the crate? We already said in the y direction, the net force is 0. Let's look in the x direction. Ooh, those look like they're unbalanced forces. We can write a nice net force equation in the x direction for part B. So that's just the sum of the applied force plus the frictional force, and we know the frictional force is pointing in the opposite direction, so you could write Fa minus FFK. All right, so these look unbalanced. The net force is gonna be equal to ma, but actually part B is just asking what is the net force. So we could just solve for the net force here. Fa is positive 200 minus 150. So the net force in the x direction is equal to 50 newtons, and the net force in the y direction is 0. So this is actually just the plain old net force acting on the object is 50 newtons. Okay, you did the vector sum between the net force in the y direction and the net force in the x direction, and it's still just the same, 50 to the right. Now part C says, what is the net work acting on the crate? Now that we know what this net force is, we can use that to find the net work. So we know that for part C, we know the work is equal to the force times the displacement. We are specifically saying, what is the net work being done? There's work being done by all of these forces. Well, actually, the normal force and the weight aren't doing any work, right? Because it's not being displaced up or down at all. But the applied force is doing some work, and the frictional force is doing some negative work because your displacement is to the right. So this is doing positive work, and this one is doing negative work. Right now we're finding the net work, the total work that both of those objects are doing together by substituting in the net force of those two forces. All right, so the net work is equal to 50, and it looks like you're traveling for 25 meters. Ooh, I forgot to write it on the side. I want to make sure I get points for the units there. So 25, and you get a net work of 1,250. And what are the units for net work? Still just going to be joules. If you do a lot of work, you could buy a lot of joules. All right, so we're going to do this problem again in a different way, and hopefully we get to the same answer. So this is another way of looking at it. Instead, we could say, what is the work done by the applied force, the work done by the frictional force, and then use those two works. We're going to get a positive and a negative work. What is the net work? And we should still get 1,250 joules. So we'll start off, I'll set this up for us like we did before. And we'll start by finding the work done by the applied force. So for part A, we're saying what is the work done by the applied force? Well, we know W is equal to F times D. And we're talking about the angle between these two vectors, the force and the displacement vector. So the displacement is 25 meters to the right this way. So what is the angle between the applied force and the displacement vector? Hopefully you can see they're pointing in the same direction. So that angle is going to be 0 degrees. And it's a little redundant to put, yeah, we're going to do cosine of the angle. Here it doesn't really matter because cosine of 0 is 1. But we're talking about the work done by the applied force. So the work done by the applied force is equal to 200 newtons, that's how much force the applied force is, over a distance of 25 meters, and the angle, again, is 0 degrees. Well, that's going to pop out a positive number for us, and the work done by the applied force is positive 5,000. And what are the units for work? You do a lot of work, you could buy a lot of joules. Okay, now that's the work done by the applied force, but the frictional force is taking away some of that energy too. If there was absolutely no friction, then yeah, you would be doing 5,000 joules of work. That's what's being added to the system. But the friction is taking out energy from the system. So how much work is done by the frictional force? Let's see. For part B, we are going to do the work done by the frictional force. And just like before, we're going to do the formal definition is FD cosine of the angle between them. And now we're talking about the force of friction. So this is the work done by friction. The little subscripts are there to help you. We already calculated, technically I should calculate the frictional force again, but we already did, and we know it's 150 newtons pointing to the left. So this is 150 times 25 times the cosine of an angle. So here is your force vector. The displacement vector is pointing to the right. What is the angle between the displacement and the force vector? Hopefully you can see that is 180 degrees, and that's what we're going to plug in for the cosine for the angle, 180 degrees. Cosine of 180 is -1, so that's going to give us a negative number, and 150 times 25 is 3,750 joules. So the frictional force is taking out this much energy from the system. The applied force is putting in this much energy. So the real question is part C, what is the net work done by these two forces? All right, so part C says, what is the net work? Oh, I was going to write net force. I'm so used to writing net force. This is the net work done by the applied force. And we could write like this, minus, because we know the direction here. And that's what I've been doing with the forces. If you want, you could go back to the basics and say, okay, this is the net work being done. Let's just add these two together because it's the total work. You sum all the work together. And then when you plug in your numbers, we'll plug in the positive and negative numbers that the cosine told us to plug in. So that's just a different way to write out that formula. So the net work is equal to 5,000, positive 5,000, plus negative 3,750. And hopefully we get to the same answer. It looks like we are. We still arrive at positive 1,250 joules of work being done. The net work of the work done by the applied force plus the work done by the frictional force is still the same thing, positive 1,250 joules. And you could, put these into your network equation too, if you wanted to find what is the work done by the normal force, or what is the work done by the gravitational force. You could write out this formula and do that as well. What angle would you plug in for theta, though, if you did all that out? You would have to plug in 90 degrees, right? Because This is the displacement. This is 90. Oh, and actually here, this is 270. So in that little example we did before, a few slides ago, we saw why those were equal to 0. So 0 joules. So yeah, the net work you could also write over here, plus the work done by the normal force, plus the work done by the weight, Fg. But that's really plus 0 joules plus 0 joules. So that's another thing to think about as well. Pretty interesting. All right, that's about it. Thanks for watching and have a great day.